Brought to you by WikiVD Documentaries. Concorde. Per Aérospatiale. BAC Concorde is a British-French turbojet-powered supersonic passenger jet airliner that was operated until 2003. It had a maximum speed over twice the speed of sound, at Mach 2.04, with seating for 92 to 128 passengers. First flown in 1969, Concorde entered service in 1976 and continued flying for the next 27 years. It is one of only two supersonic transports to have been operated commercially. The other is the Soviet-built Tupolev Tu-144, which was operated for a much shorter period. Concorde was jointly developed and manufactured by Sud Aviation and the British Aircraft Corporation under an Anglo-French treaty. 20 aircraft were built, including 6 prototypes in development aircraft. Air France and British Airways were the only airlines to purchase and fly Concorde. The aircraft was primarily used by wealthy passengers who could afford to pay a high price in exchange for Concorde's speed and luxury service. Among other destinations, Concorde flew regular transatlantic flights from London's Heathrow Airport and Paris' Charles de Gaulle Airport to John F. Kennedy International Airport in New York, Washington Dulles International Airport and Grantley Adams International Airport in Barbados. It flew these routes in less than half the time of other airliners. Concorde's name of meaning, harmony or union, was chosen to reflect the cooperation on the project between the United Kingdom and France. In the UK, any or all of the type are known simply as Concorde, with no definite article B. Concorde won the 2006 Great British Design Quest organised by the BBC and the Design Museum, beating other well-known designs such as the BMC Mini, the Miniskirt, the Jaguar E-Type, the London Tube Map and the Supermarine Spitfire. The type was retired in 2003 after the crash of Air France Flight 4590, in which all passengers and crew were killed. The general downturn in the commercial aviation industry after the September 11 attacks in 2001, and the end of maintenance support for Concorde by Airbus also contributed. Early studies. The origins of the Concorde project date to the early 1950s, when Arnold Hall, director of the Royal Aircraft Establishment, asked Maury and Morgan to form a committee to study the supersonic transport concept. The group met for the first time in February 1954 and delivered their first report in April 1955. At the time it was known that the drag at supersonic speeds was strongly related to the span of the wing. This led to the use of very short span, very thin rectangular wings such as those seen on the control surfaces of many missiles, or in aircraft like the Lockheed F-104 Starfighter or the Avro 730 that the team studied. The team outlined a baseline configuration that looked like an enlarged Avro 730. This same short span produced very little lift at low speed, which resulted in extremely long takeoff runs and frighteningly high landing speeds. In an SST design, this would have required enormous engine power to lift off from existing runways and to provide the fuel needed. Some horribly large aeroplanes resulted. Based on this, the group considered the concept of an SST infeasible, and instead suggested continued low-level studies into supersonic aerodynamics. Slender deltas. Soon after, Joanna Weber and Dietrich Kutschmann at the RAE published a series of reports on a new wing planform, known in the UK as the slender delta concept. The team, including Eric Maskell, whose report
flow separation in 3 dimensions, contributed to an understanding of the physical nature of separated flow, worked with the fact that delta wings can produce strong vortexes on their upper surfaces. At high angles of attack, the vortex will lower the air pressure and cause lift to be greatly increased. This effect had been noticed earlier, notably by Chuck Yeager in the Convair XF-92, but its qualities had not been fully appreciated.
Weber suggested that this was no mere curiosity, and the effect could be deliberately used to improve low-speed performance. Kutcherman's and Weber's papers changed the entire nature of supersonic design almost overnight. Although the Delta had already been used on aircraft prior to this point, these designs used planforms that were not much different from a swept wing of the same span.
Weber noted that the lift from the vortex was increased by the length of the wing it had to operate over, which suggested that the effect would be maximized by extending the wing along the fuselage as far as possible. Such a layout would still have good supersonic performance inherent to the short span, while also offering reasonable takeoff and landing speeds using vortex generation.
The only downside to such a design is that the aircraft would have to take off and land very nose-high to generate the required vortex lift, which led to questions about the low-speed handling qualities of such a design. It would also need to have long landing gear to produce the required angle of attack while still on the runway.
Kutcherman presented the idea at a meeting where Morgan was also present. Test pilot Eric Brown recalls Morgan's reaction to the presentation, saying that he immediately seized on it as the solution to the SST problem. Brown considers this moment as being the true birth of the Concorde project. Supersonic Transport Advisory Committee. On 1 October 1956, the Ministry of Supply asked Morgan to form a new study group, the Supersonic Transport Advisory Committee, with the explicit goal of developing a practical SST design and finding industry partners to build it. At the very first meeting, on 5 November 1956, the decision was made to fund the development of a test-bed aircraft to examine the low-speed performance of the slender Delta, a contract that eventually produced the Handley Page HP.115.
This aircraft would ultimately demonstrate safe control at speeds as low as 69 miles per hour, about one-third that of the F-104 Starfighter. Stack stated that an SST would have economic performance similar to existing subsonic types. Although they would burn more fuel in cruise, they would be able to fly more sorties in a given period of time, so fewer aircraft would be needed to service a particular route.
This would remain economically advantageous as long as fuel represented a small percentage of operational costs, as it did at the time. Stack suggested that two designs naturally fell out of the work: a transatlantic model flying at about Mach 2, and a shorter-range version flying at perhaps Mach 1.2.
Morgan suggested that a 150-passenger transatlantic SST would cost about £75 to £90 million to develop, and be in service in 1970. The smaller 100-passenger short-range version would cost perhaps £50 to £80 million, and be ready for service in 1968. To meet this schedule, development would need to begin in 1960, with production contracts let in 1962.
Morgan strongly suggested that the US was already involved in a similar project, and that if the UK failed to respond, it would be locked out of an airliner market that he believed would be dominated by SST aircraft. In 1959, a study contract was awarded to Hawkers Italy and Bristol for preliminary designs based on the slender delta concept, which developed as the HSA.1000 and Bristol 198. Armstrong-Whitworth also responded with an internal design, the M-wing, for the lower speed shorter range category. Even at this early time, both the STAC Group and the government were looking for partners to develop the designs. In September 1959, Hawker approached Lockheed, and after the creation of British Aircraft Corporation in 1960, the former Bristol team immediately started talks with Boeing, General Dynamics, Douglas Aircraft, and Sud Aviation. Ogie platform selected. Kocherman and others at the RAE continued their work on the slender delta throughout, considering three basic shapes: the classic straight-edge delta, the Gothic delta, that was rounded outwards to appear like a Gothic arch, and the ogival wing, that was compound rounded into the shape of an ogie. Each of these platforms had its own advantages and disadvantages in terms of aerodynamics. As they worked with these shapes, a practical concern grew to become so important that it forced selection of one of these designs.
Generally, one wants to have the wing's center of pressure close to the aircraft's center of gravity to reduce the amount of control force required to pitch the aircraft. As the aircraft layout changes during the design phase, it is common for the CG to move fore or aft. With a normal wing design, this can be addressed by moving the wing slightly fore or aft to account for this. With the delta wing running most of the length of the fuselage, this was no longer easy. Moving the wing would leave it in front of the nose or behind the tail. Studying the various layouts in terms of CG changes, both during design and changes due to fuel use during flight, the ogie platform immediately came to the fore. While the wing platform was evolving, so was the basic SST concept. Bristol's original Type 198 was a small design with an almost pure slender delta wing, but evolved into the larger Type 223. Partnership with Sud Aviation. By this time, similar political and economic concerns in France had led to their own SST plans. In the late 1950s, the government requested designs from both the government-owned Sud Aviation and Nord Aviation, as well as Dassault. All three returned designs based on Kocherman and Weber's slender delta. Nord suggested a ramjet-powered design flying at Mach 3. The other two were jet-powered Mach 2 designs that were similar to each other. Of the three, the Sud Aviation Super Caravelle won the design contest, with a medium-range design deliberately sized to avoid competition with transatlantic U.S. designs they assumed were already on the drawing board. As soon as the design was complete, in April 1960, Pierre Satter, the company's technical director, was sent to Bristol to discuss a partnership. Bristol was surprised to find that the Sud team had designed a very similar aircraft after considering the SST problem, and coming to the very same conclusions as the Bristol and STAC teams in terms of economics. It was later revealed that the original STAC report, marked for UK eyes only, had secretly been passed to the French to win political favour. Sud made minor changes to the paper and presented it as their own work. Unsurprisingly, the two teams found much to agree on. The French had no modern large jet engines, and had already concluded they would buy a British design anyway, as neither company had experience in the use of high-heat metals for airframes. A maximum speed of around Mach 2 was selected so aluminium could be used above this speed. The friction with the air warms the metal so much that aluminium begins to soften.
This lower speed would also speed development and allow their design to fly before the Americans.
Finally, everyone involved agreed that Kucherman's ogre-shaped wing was the right one. The only disagreements were over the size and range. The UK team was still focused on a 150-passenger design serving transatlantic routes, while the French were deliberately avoiding these. However, this proved not to be the barrier it might seem. Common components could be used in both designs, with the shorter-range version using a clipped fuselage and 4 engines, the longer one with a stretched fuselage and 6 engines, leaving only the wing to be extensively redesigned.
The teams continued to meet through 1961, and by this time it was clear that the two aircraft would be considerably more similar in spite of different range and seating arrangements. A single design emerged that differed primarily in fuel load.
More powerful Bristol Siddeley Olympus engines, being developed for the TSR-2, allowed either design to be powered by only 4 engines.
Cabinet response, treaty. While the development teams met, French Minister of Public Works and Transport Robert Buron was meeting with the UK Minister of Aviation Peter Thornycroft, and Thornycroft soon revealed to the cabinet that the French were much more serious about a partnership than any of the US companies. The various US companies had proved uninterested in such a venture, likely due to the belief that the government would be funding development and would frown on any partnership with a European company, and the risk of giving away US technological leadership to a European partner. When the STAC plans were presented to the UK cabinet, a very negative reaction resulted.
The economic considerations were considered highly questionable, especially as these were based on development costs, now estimated to be £150 million, which were repeatedly overrun in the industry. The Treasury Ministry in particular presented a very negative view, suggesting that there was no way the project would have any positive financial returns for the government, especially in light that the industry's past record of over-optimistic estimating suggests that it would be prudent to consider the £150 million cost to turn out much too low. This concern led to an independent review of the project by the Committee on Civil Scientific Research and Development, which met on topic between July and September 1962. The committee ultimately rejected the economic arguments, including considerations of supporting the industry made by Thornycroft. The report in October stated that it was unlikely there would be any direct positive economic outcome, but that the project should still be considered, for the simple reason that everyone else was going supersonic, and they were concerned they would be locked out of future markets. Conversely, it appeared the project would not be likely to significantly impact other, more important research efforts. After considerable argument, the decision to proceed ultimately fell to an unlikely political expediency. At the time, the UK was pressing for admission to the European Common Market, which was being controlled by Charles de Gaulle, who felt the UK's special relationship with the US made them unacceptable in a pan-European group. Cabinet felt that signing a deal with Sud would pave the way for common market entry, and this became the main deciding reason for moving ahead with the deal. It was this belief that had led the original STAC documents being leaked to the French. However, de Gaulle spoke of the European origin of the design, and continued to block the UK's entry into the common market. The development project was negotiated as an international treaty between the two countries rather than a commercial agreement between companies, and included a clause, originally asked for by the UK, imposing heavy penalties for cancellation.
A draft treaty was signed on 29 November 1962. Naming reflecting the treaty between the British and French governments that led to Concorde's construction. The name Concorde is from the French word Concorde, which has an English equivalent, concord. Both words mean agreement, harmony or union.
The name was officially changed to Concorde by Harold Macmillan in response to a perceived slight by Charles de Gaulle at the French rollout in Toulouse in late 1967. The British government Minister for Technology, Tony Benn, announced that he would change the spelling back to Concorde. This created a nationalist uproar that died down when Benn stated that the suffix «e» represented excellence, England, Europe and Entente. In his memoirs, he recounts a tale of a letter from an irate Scotsman claiming, "Why our talk about E for England, but part of it is made in Scotland." Given Scotland's contribution of providing the nose cone for the aircraft, Ben replied, "It was also E for Icos, and I might have added E for extravagance and E for escalation as well." Concorde also acquired an unusual nomenclature for an aircraft. In common usage in the United Kingdom, the type is known as Concorde without an article, rather than the Concorde or a Concorde.
Sales efforts described by Flight International as an aviation icon and one of aerospace's most ambitious but commercially flawed projects, Concorde failed to meet its original sales targets, despite initial interest from several airlines. At first, the new consortium intended to produce one long-range and one short-range version. However, prospective customers showed no interest in the short-range version and it was dropped. An advertisement covering 2 full pages, promoting Concorde, ran in the 29th of May 1967 issue of Aviation Week and Space Technology. The advertisement predicted a market for 350 aircraft by 1980 and boasted of Concorde's head start over the United States SST project. Concorde had considerable difficulties that led to its dismal sales performance. Costs had spiraled during development to more than 6 times the original projections, arriving at a unit cost of £23 million in 1977. World events had also dampened Concorde sales prospects. The 1973-74 stock market crash and the 1973 oil crisis had made many airlines cautious about aircraft with high fuel consumption rates, and new wide-body aircraft, such as the Boeing 747, had recently made subsonic aircraft significantly more efficient and presented a low-risk option for airlines. While carrying a full load, Concorde achieved 15.8 passenger miles per gallon of fuel, while the Boeing 707 reached 33.3 pm per gram, the Boeing 747 46.4 pm per gram, and the McDonnell Douglas DC-10 53.6 pm per gram. An emerging trend in the industry in favor of cheaper airline tickets had also caused airlines such as Qantas to question Concorde's market suitability. The consortium secured orders for over 100 of the long-range version from the major airlines of the day. Pan Am, BOAC, and Air France were the launch customers, with 6 Concordes each. Other airlines in the order book included Pan Air Brazil, Continental Airlines, Japan Airlines, Lufthansa, American Airlines, United Airlines, Air India, Air Canada, Braniff, Singapore Airlines, Iran Air, Olympic Airways, Qantas, CAAC, Middle East Airlines, and TWA. At the time of the first flight, the options list contained 74 options from 16 airlines. testing. The design work was supported by a preceding research program studying the flight characteristics of low-ratio delta wings.
A supersonic Fairy Delta II was modified to carry the OGI planform, and, renamed as the BAC 221, used for flight test of the high-speed flight envelope. The Handley Page HP.115 also provided valuable information on low-speed performance. Construction of two prototypes began in February 1965, 001, built by Aérospatiale at Toulouse, and 002, by BAC at Filton, Bristol. Concorde 001 made its first test flight from Toulouse on 2 March 1969, piloted by André Turcat, and first went supersonic on 1 October.
The first UK-built Concorde flew from Filton to RAF Fairford on 9 April 1969, piloted by Brian Trubshaw. Both prototypes were presented to the public for the first time on 7–8 June 1969 at the Paris Air Show. As the flight program progressed, 001 embarked on a sales and demonstration tour on 4 September 1971, which was also the first transatlantic crossing of Concorde.
Concorde 002 followed suit on 2 June 1972 with a tour of the Middle and Far East. Concorde 002 made the first visit to the United States in 1973, landing at the new Dallas-Fort Worth Regional Airport to mark that airport's opening. While Concorde had initially held a great deal of customer interest, the project was hit by a large number of order cancellations. The
Paris-Le Bourget Air Show crash of the competing Soviet Tupolev Tu-144 had shocked potential buyers, and public concern over the environmental issues presented by a supersonic aircraft. The sonic boom, takeoff noise, and pollution had produced a shift in public opinion of SSTs. By 1976, four nations remained as prospective buyers: Britain, France, China, and Iran. Only Air France and British Airways took up their orders, with the two governments taking a cut of any profits made. The United States cancelled the Boeing 2707, its rival supersonic transport program, in 1971. Observers have suggested that opposition to Concorde on grounds of noise pollution had been encouraged by the United States government, as it lacked its own competitor. The US, India, and Malaysia all ruled out Concorde supersonic flights over the noise concern, although some of these restrictions were later relaxed. Professor Douglas Ross characterized restrictions placed upon Concorde operations by President Jimmy Carter's administration as having been an act of protectionism of American aircraft manufacturers. Concorde flew to an altitude of 68,000 feet during a test flight in June 1973. General features: Concorde is an ogival delta-winged aircraft with 4 Olympus engines based on those employed in the RAF's Avro Vulcan strategic bomber. It is one of the few commercial aircraft to employ a tailless design. Concorde was the first airliner to have a fly-by-wire flight control system. The avionics system the Concorde used was unique because it was the first commercial aircraft to employ hybrid circuits. The principal designer for the project was Pierre Sutter, with Sir Archibald Russell as his deputy. Concorde pioneered the following technologies: for high speed and optimization of flight, for weight saving and enhanced performance. Power plant. A symposium titled "Supersonic Transport Implications" was hosted by the Royal Aeronautical Society in 1960. Various views were put forward on the likely type of power plant for a supersonic transport.
such as podded or buried installation and turbojet ducted fan engines. Boundary layer management in the podded installation was put forward as simpler, with only an inlet cone, but Dr. Seddon of the Ray saw a future in a more sophisticated integration of shapes, in a buried installation.
Another concern highlighted the case with two or more engines situated behind a single intake. An intake failure could lead to a double or triple engine failure. The advantage of the ducted fan over the turbojet was reduced airport noise, but with considerable economic penalties, with its larger cross-section producing excessive drag.
At that time, it was considered that the noise from a turbojet optimized for supersonic cruise could be reduced to an acceptable level using noise suppressors as used on subsonic jets. The power plant configuration selected for Concorde, and its development to a certificated design, can be seen in light of the above symposium topics at takeoff and to pass through the upper transonic regime and to supersonic speeds, between Mach 0.95 and Mach 1.7. The afterburners were switched off at all other times, due to jet engines being highly inefficient at low speeds. Concorde burned 2 tons of fuel taxiing to the runway, fuel used as Jet A1, due to the high thrust produced even with the engines at idle. Only the 2 outer engines were run after landing for easier taxiing and less brake pad wear at low weights after landing. The aircraft would not remain stationary, with all 4 engines idling, requiring the brakes to be continuously applied to prevent the aircraft from rolling. The intake design for Concorde's engines was especially critical. The intakes had to provide low distortion levels and high efficiency for all likely ambient temperatures to be met in cruise. They had to provide adequate subsonic performance for diversion cruise and low engine face distortion at takeoff. They also had to provide an alternate path for excess intake air during engine throttling or shutdowns. The variable intake features required to meet all these requirements consisted of front and rear ramps, a dump door, an auxiliary inlet, and a ramp lead to the exhaust nozzle, as well as supplying air to the engine. The intake also supplied air through the ramp lead to the propelling nozzle. The nozzle ejector design, with variable exit area and secondary flow from the intake, contributed to good expansion efficiency from takeoff to cruise. Engine failure causes problems on conventional subsonic aircraft. Not only does the aircraft lose thrust on that side, but the engine creates drag, causing the aircraft to yaw and bank in the direction of the failed engine. If this had happened to Concorde at supersonic speeds, it theoretically could have caused a catastrophic failure of the airframe. Although computer simulations predicted considerable problems, in practice Concorde could shut down both engines on the same side of the aircraft at Mach 2 without the predicted difficulties. During an engine failure, the required air intake is virtually zero. So, on Concorde, engine failure was countered by the opening of the auxiliary spill door and the full extension of the ramps, which deflected the air downwards past the engine, gaining lift and minimizing drag. Concorde pilots were routinely trained to handle double engine failure. Concorde's air intake control units made use of a digital processor to provide the necessary accuracy for intake control. It was the world's first use of a digital processor to be given full authority control of an essential system in a passenger aircraft. It was developed by the Electronics and Space Systems Division of the British Aircraft Corporation after it became clear that the analog AICUs fitted to the prototype aircraft and developed by Ultra Electronics were found to be insufficiently accurate for the tasks in hand. Concorde's thrust-by-wire engine control system was developed by Ultra Electronics
Thank you for watching. Brought to you by WikiVD Documentaries. Please like and subscribe below. Please like and subscribe below.